Continuing with this series of videos examining conventional physics as taught in universities and such. Something like that.
Shortly, to get a deeper understanding of the formation of the rainbows that's behind this, of course. And so you notice that the blue light is 1% slower in water than the red light. And this phenomenon that you see there, that the speed of electromagnetic radiation depends on the wavelength, depends on the frequency, we call that dispersion. It is a good thing that sound in air is not dispersive, because just imagine that high frequencies would travel faster than low frequencies, just as an example, or slower.
A very tiny difference, though, so I just don't know how it could make much difference.
For that matter. It would mean then that if you go to a concert and you would listen to the violins and the bass, that the violins would reach you first, and then the sound of the bass would reach you later. And the farther you are away from the orchestra, the worse that would be. If the effect were very strong, here in 26-100, someone sitting in the back row could not even understand my words, because the high frequencies would reach that person at a different time than the low frequencies. So sound in air is non-dispersive. But glass and water are dispersive for light, and it's very noticeable. If I take a piece of glass and I give it this shape, the shape of a prism, and I shine some light on here, light from...
So the question is yes, why is there a difference? So why is the higher frequency moving slower and slightly? And I guess the argument would be something like because the distance between the bits is smaller, so the action between hitting atoms, the momentum is different, or some other thing is different because of the speed at which you're agitating the system. Yeah, so it doesn't change as well, doesn't transfer the change at the same rate because momentum is different.
These light bulbs, or light from the sun for that matter, then I can apply Snell's law here. I know the angle of incidence, theta 1. I know the index of refraction. This is for water, but you can look them up for glass, of course. And then you will see there is a difference of the index of refraction for red light that there is for blue light. And so...
Yeah, and you also can notice, I mean, when you actually do these experiments, that the light does travel in a straight line through the material. You can see the reflections of the light. It's not waving its way across the medium. So whatever happens to the light in terms of changing its angle happens at the surface. And as it travels through the medium, it doesn't travel a curved line or something. It doesn't keep turning. So it's turned at the surface.
When you reach this side of the prism, again you have to apply Snell's law. And when you do that, you will see that the red light doesn't come out at the same angle that the blue light come out, but the two diverge. That is the result of the fact that the indices of refraction are different, but also the result of the fact that we have this particular shape, funny shape, namely that this side of the glass is not parallel to this side. And so if you put a screen here, you will see colors. You can make a spectrum. You can convince yourself that the light from these light bulbs is just not white light, but that it contains many, many colors. Well, it has to contain many colors, because if I look at that gentleman there, he's wearing a red shirt. Where do you think that red color is coming from? It must come from the light bulb, so there must be red light in there. The woman sitting next to him is wearing a green shirt, so there must also be green light in this light. And the same.
So again, not necessarily so in the sense that all it is a frequency. So what is happening is obviously a frequency is being produced. So you could throw in one frequency and you could get back different frequencies, because it's not a reflection. It's an absorption and a readmission.
It's true for sunlight. But the beauty is that making use of the dispersion, you can decompose the white light into the individual colors and make a spectrum. If you take a piece of plain parallel glass, which is window glass, then you're not going to see colors. Because if now I shine light on here, white light, from the light bulbs or from the sun, it is true that it will obviously refract in here. But when you apply Snell's law again here, then it will come out, all the colors will come out in the same direction. So the red light comes out here, and the blue light comes out in the same direction. And your brains are very special. If your brains see all colors coming from one direction, they say, I see white light. Look at the light bulb. You say, oh, that's white light, but look at this gentleman. You say, hey, it's red. It must come from that light bulb. So your brains are special in the sense that they think that the combination...
Your brains, I like that, are averaging frequencies, I would argue. So they're averaging what they're getting hit with, and the average can create white or any other color. But it's an average of what it's getting in one little area.
Of many colors is white. And I can show that to you in a rather convincing way. You see here a disk. And I would assume that you see colors on that disk. If not, you have a problem. And I can fool your brains. What I can do, I can rotate that disk.
So the disk is kind of odd. I mean, it doesn't just have three primary colors. It does have the weird dark blue and light blue and big hunk of purple. And so, you know.
So fast that your brains get so mixed up that they're going to say to you, yeah, that's white light. So let me first give you some ideal light on that disk, and I'm going to spin it up a little. So you agree with me, right? You still see colors, yeah? Still see colors, right? Okay. You still see colors, right? Yeah. Yeah. It's as white as it can be for me. Not too surprising, right? The same situation when I look at the light bulb. All these colors are processed by my brains in such a way that...
The frame rate on the video is a little slows it down, so you actually do see still some color, but yeah.
They think, or they actually make you see white light. It's as real as you can have it. And so this raises the subject of the illusion of colors, which is what I want to discuss with you for the remaining part of this lecture. If you ask a physicist, when do you see certain colors? When do you see red? When do you see blue or green? Then chances are that he would give you a standard answer, and he would say, well, that depends on the wavelength in air. If you tell me what wavelength you're on, then I will tell you what colors you will see. And I have here a transparency which makes the connection between wavelength and these colors. It's also on the web, so you can also download this. And so if the wavelength of light in air is about, in this range, 1 angstrom is 10 to the minus 10 meters, yeah, you will probably say that's red light. When the wavelengths get shorter, in this range, you would say, yeah, that's green light. And when the wavelengths gets even shorter, you would say, yeah, that's blue light. And you can't see any wavelength shorter than this. You get into the ultraviolet here, and you can't see any wavelengths longer than this. That's infrared, and our eyes are not sensitive for those wavelengths. So this is all nice and dandy, but we still have the problem of the fact that if you mix all the colors together, like the rotating disk, and like looking at the light bulb, that our brains still tell us that we are seeing white light. So maybe matters are not really as simple as we think. And this scheme about colors has been worked out in quite some detail already in the 17th and in the 18th century, when it was discovered that there is such a thing as primary colors. Maxwell did some research on that. And Helmholtz, even the poet Goethe, did work on this. They discovered that there are primary colors, and when you mix light, we call this additive mixing. The three primary colors are green, violet, and red. And when you mix paint, the three primary colors are yellow, blue, and red. And the idea behind this is that if you mix the three primary colors in the right proportion, that you can make many colors. I want to show you.
You can make many colors, yes. Yes. But they're averages.
To a colored triangle, which is the recipe, tells you how you have to mix these colors. And in order to do that, we're going to make it dark, but not all the way dark. So here you see the colored triangle. And the colored triangle has in the three colors, the three corners, the colors red, one primary color, and then here it has violet, and then up there it has green. And now I'll tell you how this recipe has to be used. So I'm going to draw here the colored triangle. And we have red here, and we have green there, and we have here violet. If you look at this color triangle, you see all the colors that you can imagine, sort of. You see yellow, and you see here purple, and you see orange. You even see white. So how do we make these colors now? Well, suppose I want to make this color here. So that's this color, say. Then you draw 3 lines. 1, 2, 3, from the 3 corners. And this is the amount of red that you have to put in. And this is the amount of green that you have to put in the light. And this is the amount of violet.
Yes. So, I mean, you know, it's almost like doing a center of gravity kind of thing, except you're basically just pointing out how the distances are proportional to. They can't get to that spot. If you did this geometrically, you know, that spot has this certain rules. So, yeah, it's a nice little trick.
Light. And if you do that in that ratio, you would get the color which is here. If you want to make very nice yellow, oh, let's see, let's make some very nice yellow, which is all the way here at the edge. You don't need any violet. You can do that exclusively with green and with red. So let's go to this point here, which is yellow. It would mean then that I have to put in this much red, and I have to put in this much green. And if I add more and more red, I go along this line, then I end up here and I get orange. So I could make orange here by simply increasing the amount of red. Oh, this should not be violet, right? This is green. Oh, you should have yelled at me. So this is green. And so if I want to make orange here, then I simply have to give it more red and less green. And if you go to an extreme and you want to make white light, and you go bingo right there in the middle, well, then you have to give it this much red, this much green, and this much violet. And that's the idea that we just saw. You mix all the colors, and we mix up your brains as well, and your brains then say, gee, yeah, that is white light. So the idea behind the 3 primary color theory is that our eye cells, the cells that we have in the retina, respond differently to the 3 primary colors. And that color sensation, which is of course what the brains are telling you, those are the messages that are being sent to the brain, that they're processed here, that they are the result of the mixing of these 3 responses. And this theory is quite successful. I'm going to try to make for you the color yellow by mixing these 3 colors, green and violet. And if I want to make yellow, then we already argued, all I need is green, and I need red. I don't even need violet. And I'm going to do that with this nice little box.
Right, so you're just taking frequencies, and the frequencies are going to be less than the highs and more than the lows, and that'll be white light, would be somewhere in the middle in terms of averaging those frequencies. Something like that.
Box here, I will raise the screen because we don't need the screen anymore. And I don't think I need the slide anymore, John. And this box has 3 lights in there. Red, green, violet. And I can change the intensities. Yeah, I can show you. I can make the red less strong, and I can do the same with the green. I can make it less strong, and I can do the same with the violet. And so if I want to make, for instance, that yellow, then I can do that with green and red alone. And I have to give it a lot of green and a little bit of red. So a little bit of red and a lot of green. Adjust it a little. I see yellow. Don't you? Who sees yellow?
Greeny yellow.
Okay. Shall we make it a little orange, and we have to give it a little bit more red? Yeah, I give it a little bit more red. Oh, it comes orange. See, so I'm marching now here, give it a little bit more red, and you make it orange. And what I can even do, I can give them all 3 the maximum strength, and I can turn it to white. So you fool the brains again. All these colors, like the rotating disc, like the light from the sun, like the light from the lights here. I think I see white light. Your color TV is based on this principle. You have 3 electron guns in your color TV. And there are 3 different chemicals on the screen of your television. And these chemicals are in the form of very small dots. And if electrons hit one of these dots, they become violet, and the other chemicals become green, and the other chemicals become red. And so the whole idea is now that each beam hits its own chemical dot. That's the way they arrange things. And by mixing the various intensities, you can mix the intensities of the three primary colors, and you can see all colors on television. It works very well. Of course, if you haven't adjusted your television properly, you may have noticed that sometimes faces are reddish or faces are greenish. Well, that's a matter of just adjusting those three guns appropriately, and then you can be very successful, and it's very impressive. This three-color scheme works quite nicely. So in many cases, the three primary color theory is quite satisfactory. But there are cases where it fails bitterly. And those are the ones that I want to discuss for the remaining 10 minutes and 40 seconds.
Good. Unfortunately, though, it's not going to be enough. There's not going to be any answers, just questions.
Already in the 19th century, it was known that there were problems with the three-color theory. Mr. Benham, in 1895, invented a top which is named after him. It's called the Benham top. I have one in my office on my table. It is a top that has just black lines on it, no colors. You rotate it, and you see colors. And we copied that top for you, and we have that here. This is
Well, it does have colors in the sense that the white, we've already established that when you're seeing white, you're seeing the three primary colors. So it does have colors when it's black and white. You're just not seeing the colors.
a copy. It's a large copy. The top is only this small that I have. This is a Benham top. I hope you will agree with me that this is black and white. Any one of you see colors? Let me know now. I will ask you to leave then. Okay, so no one sees colors. Good. So now I'm going to rotate.
But again, like I said, the colors are there. We know just like when the other thing was spinning, the thing next to it, it turned white. So the colors were in the white. So the white is full of colors.
That's for you. And you'll be surprised what you're going to see. So there is the Benham top. And I'm going to rotate it somewhere in the ballpark of about 7 hertz, 5 to 7 hertz. Let's take a look. Black and white. Hey, Popple Pay, what am I seeing? I'm seeing colors, not very bright, but I am seeing colors. I see some rusty brown right there in the middle, and then I see something with grayish green maybe and dark blue further out.
Right, and so the point would be is you're seeing that because of the frequency of the lines moving. So the lines on the outside are moving faster than the lines on the inside. So you can sort of intuitively say they're changing the frequency, they're interrupting the frequency of the light by more in the outside than on the inside. And so they're basically doing a prism thing in a crude way, and that's why you're getting the red in the middle, and the red inside and the blue on the outside. It's because of the speed difference.
Who sees colors? Who doesn't? Oh, you're colorblind then, that happens. Well, you see colors just with black and white rotating. And to make it even worse, I can reverse the disc. First have to stop it, otherwise we burn out the motor. And I can reverse it. Remember the rusty brown was in the center. Now we're going to rotate it the other way around.
Oh, okay.
Look
Never
again what you
mind.
see.
Never mind.
You're now seeing the rusty brown near the edge. You see the colors reversed.
All right, but it still has something to do with obviously the length and the speed. You could argue that the lines are longer on the outside than they are on the inside, and that would be proportional to the speed of the wheel. So then they'd all be the same length technically in terms of what you're going to perceive because of the speed difference. So that sort of makes sense. The interruption. So it's taking white light and subtly changing, like splitting it in half almost, it's cutting the frequency by these little percentages. And so it's just breaking the white light, which is the average, right? So if we say white is a perception of an average, somewhere between the 700 and the 350, let's say, if we use those numbers in nanometers, and we say white is when your brain averages that, then it's just changing that average.
A lot of research was done in this area, but a complete neurophysiological explanation is still not available yet, even though there are several very successful models that can predict what our brains will see. When your color cells are stimulated with flicker light, there are phase delays between the incident light and the response, the messages that are sent to your brains, which are currents, of course. And the phase delay is different for different colors. So what we're doing here, we're fooling the brains. We're sending flicker light to the brains with different phase delays. The phase delays in the center are different from the phase delays further out. And so the brains then process that in the usual way, and they say, well, I'm sorry, but you're going to see colors. And that's what you're seeing.
I guess it's a complex way of saying something similar to what I'm saying, is that you're changing the perceived frequency. Simple enough.
The most fabulous example of where the three-color theory fails, or at least is very incomplete, is the work done by Edwin Land in the early 50s. Edwin Land, very famous man. He was the inventor of the Polaroid film. He pioneered color theories and became very famous for a particular demonstration that I will do for you here. He gave me 2 slides. I got them personally from Edwin Land. And these 2 slides that I'm going to show you are black and white slides. That is non-negotiable. I'm going to show them to you. They're as black and white as this disc. He took one of those slides.
Let's remember again, white isn't nothing. It's something. It's full of colors. White.
Taking a photograph of something. What that something is, you're going to see very shortly. And the other black and white slide, he also took, again, black and white film, but he put a red filter in front of his camera. But believe me, it is a black and white slide. So you're going to see 2 black and white slides. And then I'm going to do something special with those slides. And therefore, I'd rather go there now.
So you have just the white light of the camera and then some diminishment of how much light's getting through. So black and white really isn't black and white. It's just a lot of white or a little bit of white, you know, when it's going through a slide. You're just blocking how much light gets through in black and white film.
And then explain things to you as they come along. And so I have to make it very dark. Oh, the screen has to come down, of course. We're going to need the screen because we're going to see slides. So 2 black and white slides. So the first black and white slide is this one.
Okay, so it's lifesavers and then a picture of a clown. And so again, it's the white is light coming through, and the darks are less light. The grays and all the other colors are just less light getting through.
I hope we will all agree that this is a black and white slide. And the second black and white slide is of the same scene. This, by the way, was taken through a red filter. But it is black and white. The next one was not taken through a red filter. But, I hope we all agree, it's black and white. If I put a red filter in front of this black and white slide, you see exactly what you would have predicted. Namely that, yeah, it's like looking through a red piece of glass. The whole world turns a little reddish. Very boring, although some kids like that. So this is what you're going to see. I can do the same with the other one. This is the one that Edwin Land photographed through a red filter. If I put a red filter in front of it, you're going to see what you expect. Reddish, pinkish colors. Okay. What do you think you're going to see if we project one black and white slide on top of the other black and white slide? Well, let's face it. Let's be down to earth. Black and white plus black and white will remain black and white. And that's what you see now. One is now on top of the other. You may not notice that, but I will take one away and add it again.
All right, so you do get a lot more variation. You can see his hair now, so there is more color. There's more shades of gray. His nose, lots of things are now much more pronounced.
Black and white plus black and white gives black and white. Now I'm going to ask you to sit very firm in your chairs, because you're going to fall off your chairs if you're not careful. I'm now going to put in front of the slide that Edwin Land took through a red filter, I'm going to put that red filter in front of my projector. Only through that slide. The other one remains as it was. And there we go. And now what do you see? You see colors. Is this a miracle? Or maybe it is.
Well, you see one color more than other colors for sure. The red, obviously. And yes, you see some hints of other colors. So again, it's not exactly, but yes, interesting. Yeah, that's all I can say.
I see yellow here. I see green here. I see some dark blue. Who also sees colors? Just say yeah. Who doesn't? Good for you. Isn't this amazing? 2 black and white slides. That's all you're seeing, and then you see this silly red filter, which normally would give you only a little bit of pinkish reddish light. But when you put one on top of the other, something bizarre is happening in your brains.
Be interesting to see what happens with other colored filters, like a green filter or a blue filter, just to see what if you get any differences in the intensity of any of the colors.
Your brains are so incredibly mixed up that they really think you're seeing yellow there, and they really make you think that you're seeing green there. A reasonable question now is to ask, if we took a picture of this, you take your camera with color film, what will you see? Will you see colors or will it be black and white? Yes, you will see colors, but the colors will be different from the way that you and I perceive them right now.
Well, that's sort of interesting. I don't know how much different, but I mean, obviously the video has recorded them accurately because it's, the frame rates and all that kind of crap, so I'm seeing a recording of a recording kind of thing. So the colors must be there.
So now you can ask yourself the question, well, what are now the real colors? The ones that you and I see, or the ones that our picture will record? Well, I think that's a meaningless question. There is no such thing as right or wrong in this matter. Our brains are very complicated. And whatever they show us, that's the real thing for us. Reality is very relative.
Yeah, well, that's sort of nonsense. There's obviously a frequency. There's obviously pixels producing a frequency, and the frequency, again, is an average. And there's a certain reality, a certain truth to what frequency the pixels of light have.
And if you're colorblind, which quite a few people in my audience must be, just a matter of statistics, then they have a different reality altogether. Reality is only in the mind of the beholder. And it all depends.
Yeah, well, that's just rubbish. So anyway, so the lecture ends with rubbish statements. There's a truth here. It doesn't have to be left unanswered.
On how your brains are processing messages. The message that I'm giving you for this weekend is, have a good time, but by all means start working on your exam 3, which certainly is not an illusion.
Yeah, so interesting stuff. So I didn't have much to say about it, but it's just interesting. Nothing to contend because nothing much exerted. Again, just keep in mind that when he says black and white isn't void of color. It's got colors on top of each other, and it doesn't seem unreasonable that you could separate that on topness and reveal that there's colors in the white. So anyway, yeah, that's enough to be said. So the next time, like I said, these lectures, these last few are interesting, getting into all this photon stuff. Anyway, till next time.